Okay, this is section 10.3. Logarithms are exponents. So in 10.1 we had the exponential equation, b to the x equals y. 10.2 we learned about inverse, so if I took the inverse of this, it would be b to the y equals x. That y is pretty tricky to solve for, and so, which would be our next step in finding the inverse. And that's where this definition of a log comes in for. So if b to the y equals x, that's going to be equivalent to log base b of x equals y. So in log form, let me write this a little bit bigger down here. Here's our log form, log base b of x equals y. And that means the same thing as b to the y equals x. So logs are exponents because logs equal the exponent in this equation. And so this one is still a log because it's the y that's the exponent. In an exponential, it's going to be the x that's the exponent. So these are the same thing. They're just two different forms of the same thing. And you'll see sometimes it's handy to have one or the other. Okay, so now that we got some numbers in here, let me try to explain what logs are. And this problem is we're supposed to write this in exponential form. So we had that log base b of x equals y. That's our log form. And they're asking us to write it in b to the y equals x. So let's take a second and just kind of look at the pieces of this and figure out what logs are actually doing, rather than all this crazy stuff, because it makes way more sense with some numbers. Log base 7 of 49 equals 2 is how that reads. And what the word log means, because if you think about mathematical symbols, they go with, there's some words associated with them. And so the words that go with log are, what do I raise this base to in order to get this number? And then the answer is that exponent. So in this case, what do I raise 7 to get 49? So that's what log means. Log base 7 of 49 is saying, what do I raise 7 to get 49? And that answer would be 2. And so if I take that, and so basically the exponent is the answer. And the thing we're used to being the answer is now given very often. So this is in log form. So if I write an exponential form, I kind of think of it as 7 raised to the second equals 49. That little swoopy thing works pretty good for me. So 7 raised to the second equals 49. And they may have a thing in the computer where it's like A, B, C or something, and you let A, you type in 7, B, you type in 2, and C, you type in 49. I don't know why they don't just have you type the thing, but I think there's some kind of crazy entry on that one. This one's the same thing, so again, I'm just going to do a little swoopy deal. So 5 to the negative 3 equals 1/125th. So 5 to the negative 3 does make 1 over 125. The second set, now we're in exponential form, and we're trying to get to log form. So for that one, the way my brain looks at it is the base of the log and the exponential stay the same. So it's going to be log base 4. And it's these other two things that are swapping places. The answer becomes, the exponent kind of becomes the answer. So it's 64, and then the exponent is here. So it's kind of almost like it's, if it was 4 to the 3 equals 64, it's like I'm thinking of these two things swapping sides. So this one, log base 6, 136 is on this side now, and negative 2 is on that side because our exponents are our answers. So this next round is solve for x. And in these log equations, it's really hard to look at that and kind of get your brain around it. But if we rewrite it in exponential form, it's much easier. So 3 raised to the 4 makes x, or 3 to the 4th equals x. So this is asking what 3 to the 4th will make the value inside. And that's just 81. Here, number 4, this is going to go 25 to the x makes 5. So 25 raised to the x makes 5. If you can see it's 1/2 right there, you're golden. If you're having a hard time seeing the 1/2, here's a little trick to doing it. 25 is the same thing as 5 to the 2x, because 5 squared is 25. So I'm just writing 25 as 5 squared with the x. And then that lets me write this side as 5 to the 1. So once I have a common base, 5 to the 2x equals 5 to the 1, 2x has got to equal 1. Now I can divide that over, and x equals 1/2. We'll be using this technique later in the chapter, so definitely worth looking at here, even if you can see what the answer is. It's still a very useful technique. This one we got x squared equals 9, and so if I root both sides, and again the base has to be positive, so I don't have to worry about a plus minus. That's going to be x equals 3. And then this one's a little tricky. So 36 to the x equals 1/6. 36 to the x makes the 1/6. So 36 is 6 squared x, and 1/6 would be 6 to the negative 1. And now I can set those equal and then divide over the 2 and get x to the negative 1/2. Okay, and these would be the matched questions. So this is right in exponential form, so we're going 13 to the negative 1 equals 1/13. This is going to be 2 to the 5th equals 32. Right in log form. So this is going to be log. Remember the base stays the same, and the other two switch sides. The exponent's the answer, because logs find exponents. And then here we'll have log base 2. The 1/8 comes over, and then equals the exponent, negative 1/3. Or sorry, negative 3. And then these are the matched solve ones. So 9 squared equals x, or x is 81. This would be 27 to the x equals 3. So 27 raised to the x equals 3. And then, again, if you can see the 1/3, cool, just go there. If not, 3 to the 3x and 3 to the 1. So I'm just writing 27 as 3 cubed and showing the exponent here. 3x equals 1 and x equals 1/3, or cube root. For this, 2 to the negative 3 equals x. So that would be 1 over 2 cubed equals x, or 1/8. And this would be 10 to the x equals 100. So what do I raise 10 to get 100? I'm sorry, 100th, my bad. So this, it's going to be a 2, right? Because it's going to 100. And then I think it's almost easier just to kind of recognize the negative 2 than to bring the 100, because the 100 would be 1 over 10 squared. And I could bring that up and then show that 10 to the x is 10 to the negative 2, and then x is negative 2. But I think it's easier if you just kind of go 2 and then go, it has to get downstairs, so it must be negative, rather than going through all that. So these are simplified. They're not equations. This is just a number that can be turned into a number. That said, sometimes, especially as you're first learning logs, it's really hard to look at this and make sense of it. It would read, what power do I raise 8 to get 64? So the answer would be 2. But if that's difficult, and it often is, you can throw an x over here and then write it in exponential form. And sometimes just the visual of being able to see it that way, then you're like 8 to the, 2, x is 2. And it's because this is 8 squared. But so I think sometimes rewriting it in a more comfortable version can help to see how to solve them. So this is, what power do I raise 5 to get 5? Or if I did the trick with the x, 5 to the x equals 5. So x has got to be 1, because that's 5 to the first. What power do I raise 8 to get 1? If you can see it, cool. If not, 8 to the x equals 1. So that has to be 0, because anything to the 0 makes 1. This one, what do I raise 8 to get 16, is not the easiest thing. So that one, we're going to definitely want to use the x. So this is going to go 8 to the x equals 16. And careful, it's not 2. 2 times 8 is 16. 8 to the 2, 8 squared would be 64. So this is a great place to use that base, the common base trick. So we're going to go 2 cubed x equals 2 to the 4th. And 3x equals 4. And now I can divide both sides by 3, and x equals 4/3. So it's one of those fractional exponents where we take the cube root of 8 and then raise it to the 4th, which would be 16. And this one is just sort of practice thinking through the they're just numbers, so what they actually mean. So I'm going to write down these front couple logs and just do kind of inside to outside. So log base 2 is 16. That means what do I raise 2 to get 16? So this is just a big fancy 4, because 2 to the 4th makes 16. And then here, what do I raise 4 to get 4? 1. And here, what do I raise 6 to get 1? 0. So it's a very, very fancy 0. Okay, and these are the matched problems. So what do I raise 3 to get 3? 1. So that's just, that whole thing means 1. What do I raise 7 to get 1? 0, because it's the exponent that I would raise 7 to. So 7 to the what? 0 makes 1. This one, what do I raise 9 to get 27, is the not easy one. So 9, we'll invent an x, equals 27. So 3 squared is how I'll do the 9. And then 3 cubed is how I'll write up the 27. So 2x equals 3, and x equals 3/2. If we go back, it makes sense, because 9 to the 3/2 would be square root 9 is 3 cubed, and there's our 27. This one, so we got the log 2, log 4. This is what do I raise 3 to get 81, so that would be another 4. I should have made this one more different. Oh well. What do I raise 4 to get 4? So 1. And what do I raise 2 to get 1? It came out 0 again. Okay, so we got some definitions, and I forgot to print this. So if I have log base 10 of x, it's kind of like having a square root, how we don't write the little 2 in the index. So plain log x is going to be the same thing as log base 10. So when there's nothing there, it's an implied 10. Natural logs. So there's going to be this mysterious number e, and I'll talk more about that when we get there. But something that is log base e of x is going to be ln, or log natural. That's not an I, it's an L, so lnx. And this e is this 2.718. It's kind of like pi. It's an irrational number. It goes on forever. And it ends up being super handy. And so we'll do just a little bit within this course, but it'll definitely come back in future courses. And then we get change of base formula. And I'll do this when we get to a problem. So this first part is just finding the log button on your calculator. And so if you find the log button, try, and this is your base 10, because there's that implied 10. If you plug that in correctly, you should get 1.5775 to 4 decimal places. And yours could be log number or number log, so you just have to kind of play with it and figure it out. ln of 23, natural log of 23, is going to be 3.1355. So find that button and make sure you know how that works. So here's the change of base formula. If I have something that is, I'm going to scoot over here with it so I have room, log, let's see, we'll go log base b of x right here. I can go log 10 of x over log 10 of b. I could also use natural log. I could use a log of any base. Usually we just use log base 10 if it's handy. But the way I think of it is sort of log of the top number over log of the bottom number. So that's going to be log base 10. I'll just leave it blank there though. 22 over log 5. And like I said, I could natural log 22, natural log 5, or any other base that I want. If you get that successfully into the calculator, that should come out to 1.9206. So this next round is using those ideas to solve some little equations. So this is an invisible 10 right there in the base. So this is going to be 10 to the 4.8802 equals x, if I write that in exponential form. And then you just plunk that in the calculator, and I got, that is a big number, x equals 75,892.6993 to 4 decimals. This one, so it's base 10, but then this side's kind of crazy, so let's just write this as log base 10 of x for a second. But this is just a number, there's no variable over here. So what power do I raise 3 to get 81? That would be 4. And then now when I change it over to an exponential, it makes sense. 10 to the 4th equals x. So that's going to be a 1 with 4 zeros, or 10,000 equals x. And then the other thing is that 10, you can do 10 caret or exponentiate. Sometimes they do that for the button on the calculator. But if you look at the second function of the log button, I bet it's 10 with a raised 2 already set up. For this one, we're going to also be looking for the second function. So if you find the ln button, you should see an e to the x button as a second function. It's almost always the second function of the natural log button on your calculator. So this is an invisible e down here. So this is e squared equals x. So e to the second makes x. And when it's something nice like that, I think the computer wants it as e to the second. And this is just standing in for some kind of ugly decimal. This one, which is similar but now has an ugly decimal, that one I think they're looking for a decimal approximation. So e raised to this is going to make x. So e to the 3.459 equals x, and that's going to be 31.7852. Okay, I'm going to skip the next 3 because they're just the plug into the calculator ones again on the matched problems. And then I'll just do these last 4 solves. So this would be 10 to the 3.98 equals 9549.9259. This would be log base 10 of x. What do I raise 2 to get 8 would be 3. So 10 cubed equals x. So this would be 1000 equals x. Here, this would be an invisible e. So e to the 4th makes x, or e to the 4th equals x. And another e right there, so e to the 4.51 equals x. Again, when it's a decimal, I think they want a decimal approximation. So this would be about 90.9218.